Okay, so welcome back. So here, now what I will talk about is basically the part which is about the solution. Okay, you have a solution. Okay, you have a solution in a closed cell, hmm? And this cell has length L and area A. Okay, cell of length L and area A, cross sectional area A. Okay, now I passed electricity through the solution. Okay. Now this solution, okay, definitely if I get here electricity output, that means this solution can conduct electricity. Okay. Now according to, if instead of a solution, if I put a wire here, then at the end of the wire, okay, at the end of the wire between the two potential difference VA and VB, what you will find? You will find electricity, and according to the Ohm's law, V is equal to I into R, right? This is for a wire. Okay. Similarly, this solution will also have a resistance, right? Also, the solution will also have a resistance. Okay. But this resistance, what we know, this resistance, we are not interested. Okay. But what we are interested is basically the conductance, the conductance of the solution. That means the conductance is what? Conductance is basically the reciprocal of the resistance. Did I say the conductance is basically defined by G, which is nothing but 1 by R, right? Conductance G is 1 by R. Now, this conductance, if I think about, if this conductance, what I'm measuring for the solution I'm measuring, and the solution is where? The solution is in a cell which is length A and cross sectional area. Okay. So what will be the conductivity? The conductivity of the solution, conductivity of the solution, okay, the conductivity of the solution which is defined by kappa, okay, kappa, this conductivity of the solution will be dependent on the conductance as well as the length and area of the cell, okay, where the solution is present, which is defined as G multiplied by L by A. And you know what this L by A stands for? Cell constant. Okay, cell constant. Hmm? Acha. Now here, what I can write here, kappa is equal to 1 by R multiplied by L by A. Okay, so this is the conductivity of the solution. Okay, kappa is equal to 1 by R into L by A, and kappa is equal to G into L by A. So this will be a helpful thing. Okay, now, okay, now if I think this one, okay, so what is this conductivity and conductance means? If I say, okay, what is the definition? If I put, let's take this expression, kappa is equal to G into L by A, right? This is the expression. Now let's put that if I take a cell, if I take a cell where L is your 1 centimeter and A is your 1 centimeter square, okay, then what will be the cell constant? Is 1 centimeter divided by 1 centimeter square, that is centimeter inverse, right? This is the cell constant, 1 centimeter inverse. Okay. Now, if it's 1, so then your kappa will be equal to G, right? The kappa will be equal to G. That means what is the conductivity? Conductivity is of an electrolyte solution. Definitely this will be an electrolyte solution, because until and unless it is electrolytic, it cannot conduct electricity. For an electrolyte solution present in a cell of 1 centimeter length and 1 centimeter square cross-sectional area, the conductivity is defined. The conductivity of the electrolytic solution is known to be the conductance. Okay, so K is equal to G. Right? Okay. Now, what is the unit? What is the unit of conductance? What is the unit of conductance? G. What is the unit of conductance? R. The unit of R is ohm. So 1 by R is basically your ohm inverse, and which is M into mho. Mho. Right? So this is basically 1 Siemens. 1 Siemens. Right? Hmm? So what is the unit of then your, okay? Now if I put here together, what is the conductivity? The conductivity is, one unit of conductivity is Siemens. Okay. Now this conductivity, this is conductivity for a cell where you have an electrolytic solution. Okay. Next question will come into everyone's mind, that this conductivity depends on which factors. How will I modulate this conductivity? Let's see if I'm trying to measure the conductivity of a solution. Okay. Then how will I do some experiments and modulate this conductivity in the different forms, different conditions, and I will be easily able to measure the conductivity. Okay. So next point is that what are the factors, important factors, okay, which affects the electrolytic conductance or the conductivity. Okay. Write it down one by one. Okay. Factors affecting conductance of electrolyte. Okay. Factors affecting conductance. Number one, if we think very clearly here, the one major factor is the substance itself. Is the substance itself. Okay. Now the substance can be two types. It can be a strong substance and it can be a weak substance. Right? The strong substance is called a strong electrolyte, and the weak substance will be termed as weak electrolyte. Okay, so weak electrolyte. Now what is a strong electrolyte? A strong electrolyte is an electrolyte which dissociates completely in the solution, and weak electrolytes are the substances, electrolytes which dissociate, which has performed incomplete dissociation. Okay. Examples you have learned already: HCl, NaOH, right? For weak electrolyte, acetic acid, ammonium hydroxide, right? So these things are known as a weak electrolyte. So there will be a form of incomplete dissociation in the solution, and due to the incomplete dissociation, the conductivity will be also low. And due to the strong dissociation of HCl and sodium hydroxide in the solution, the conductivity will be more higher. Okay. Acha. Now next question, next point is the solvation. Solvation. Let's say if I take the aqueous solution of this solution, let's say I take AB aqueous solution. So what this aqueous solution means? It means that if you have A as a cation, this A will be solvated by the water molecules. So this is known as a solution. will be solvated by the water molecule. Similarly, B also will be solvated by the water molecule. Now, if this solvation, if this solvation is very high, okay, if this solvation is very high, then what will happen? This A molecule, these A ions will have a difficulty in move, difficulty in moving, right? They will face very difficult situation while moving because they are already solvated. Like in think in this way, you are moving from one place to another place, and your people you were tied by a rope, and people are pulling you. Okay, so you will find very difficult way to move from one place to another place. Similarly, here also, the solvent molecules, if this A and the A or any other electrolytes are more solvated by the water molecule, they will be find very difficult to move or conduct electricity from one place to another place. So in that case, your overall the conductivity, the conductance of the solution decreases. Hmm. Next factor, which is temperature. Temperature. What will be the temperature effect? Now, if you increase the temperature, the kinetic energy of the molecules increases, right? The kinetic energy increases because kinetic energy is a function of temperature. The kinetic energy increases, and if the kinetic energy increases, this ion becomes more mobile, okay, more mobile and move faster, and as a result, your conductance. So in temperature, the conductance is proportional. Hmm? Last point. Sorry. Last point. Viscosity. What is the factor of viscosity? See, the viscous solution means what? If you refer to my liquid state solutions, the first lecture, which is on liquid state and viscosity, what does viscosity mean? Viscosity means it's a process where you have solution layers and one layer will obstruct other layer to move. And this force, by this force, is increases from upper to lower. Okay, and the velocity of the each layer decreases one by one. Means one person is basically means stopping the other layer to move. Okay, so this is known as the viscous force, and this phenomenon is the viscosity. Now, what happens in this case if you have like similar, if you have high viscosity, what will happen? The high viscosity, the ions will try to move, but due to the high viscosity, their movement is very low, right? And as a result, what happens? As a result, your conductance decreases. So higher the viscosity, lower the conductance. Higher the viscosity, lower the conductance. So these four are the very important factors which controls the electrolytic conductance of the solution. Okay? Acha. Now, moving on to the next part. Hmm. Moving on to the next part where you use a particular condition where the substance, the electrolyte substance you take, okay, the interest substance you take, and that substance has a particular concentration, definitely. See, your concentration, if your concentration is high, okay, then the conductivity definitely will increase, okay. But that concentration, how will you represent that concentration? That is very important here. Okay. So there are two ways of representing the concentration here, and that concentration will give you a particular way of defining the conductance of the solution. Let me show you how. Show you how. Okay. Let me show you how. Okay. Say in the first case. Okay. What I'm defining, you have two electrodes. Okay, two electrodes, hmm, and these two electrodes dipped in a solution, and sorry, these there is a solution between the two electrodes, okay, and they are 1 centimeter apart. Okay, they are 1 centimeter apart. 1 centimeter apart. Acha. Now, okay, now, so let me write here large electrodes are 1 centimeter apart. Okay, and solution of electrolyte present in between them. Present in between them. Okay, the solution of electrolyte present in between them. Okay, now what will happen here? So this part has a particular volume. Let's say the volume of the solution is V, right? The volume of the solution is V. So let's define a your conductivity. Define a conductivity by lambda. Okay, lambda, and this lambda is basically what? This lambda will be equal to kappa multiplied by V. Okay, now if I use volume here, and with your conductivity K, conductivity kappa, that means the conductivity I am defining per volume, sorry, in that volume. Okay, so this is known as the lambda m, which is known as the molar conductivity. Okay, molar conductivity. Now this lambda m, and instead of this, what if I give the molar conductivity, then K will be into multiplied by 1000 by C, where C is the concentration in molarity. C is the concentration in molarity. In thousand ml, here C is the molarity. So instead of volume, what I am writing 1000 by C. So what is the definition of lambda m? Lambda is equal to 1000 kappa by C. This is the molar conductivity. Okay. Now, what is the unit of K? What is the unit of K? K unit is your Siemens centimeter inverse. Okay, and unit of C is your mole per cc. Moles per cc. So what is the unit of lambda m then? Siemens centimeter inverse mole centimeter minus 3. So this is will be equal to Siemens mole inverse centimeter square. This is unit of lambda m. Molar conductivity is Siemens mole inverse centimeter square. Okay. Acha. Now if I do this in this way, same thing. Oh, excuse me. Instead of giving the C concentration, I can dissolve case 2. This is first case. Second case, I can dissolve one equivalent of solution electrolyte. One equivalent of electrolytic solution. If I dissolve between the 1 centimeter apart electrode. Okay. So in this case, what I can write mathematically, I can write lambda is equal to kappa by into V, right? And instead of this V, what I can write here will be equal to kappa. So equivalent means, now go to the your solution second lecture where you have defined molarity, normality there. So in this case, the equivalent to it, your volume, now your concentration will be expressed in normality because it is one equivalent, and normality comes where your equivalent One equivalent is your there in the one equivalent of solute is present in the solution. Okay, so this will be 1000 in 1000 ml divided by your, instead of C, what I will write, N, where N is your normality, right? N is your normality. Okay. Now, so what is this? Hmm? So what is this? This is known as lambda EQ, and this is termed as equivalent equivalent conductivity. Okay, equivalent conductivity, equivalent conductance, whatever you say. Acha. So this is unit. What will be the unit? Same, Siemens, centimeter inverse. But instead of normality, here what I will write? Equivalent, equivalent centimeter cube. So what is the unit getting? Siemens, equivalent inverse centimeter square. So this is a unit of equivalent conductance. Okay. So what you have learned here? If I express the concentration in molarity, so it will be the molar conductivity, molar conductance. And if I express the solution in case is conducting one equivalent amount, which is a normality, it is known as the equivalent conductance. Okay, so these all. So what we have learned: conductance, conductivity, resistance of the solution. Okay, what are the factors which controls the conductance of the electrolytic solution? Okay, and we have learned the molar conductivity and the equivalent conductivity. Now, this part, what you will expect? Numerical. Okay, and conceptual things. They can ask you definitions of molar conductivity, equivalent conductivity. Okay, and mostly you will encounter numericals. And the last lecture in this lecture series, at the end of this electrochemistry chapter, I will give you one video lecture where I will discuss all the problems. Okay, not now. I will discuss all the problems related to the all the problems, mostly 90% numerical problems related to this chapter, where you will find these equations will be there. Okay. So till then, thank you.